Okay. Yeah, so again, this is a topic that we are going to begin now, and we will continue in January. That is the first law of thermodynamics. And as we do this, we need to review what energy is and how that actually relates to work. So we'll do that at the beginning. We'll do a couple of problems relating work to energy and vice versa, and then we'll actually talk a little bit about what are we actually talking about when we talk about doing work. So our first question: what is energy? What is energy? And we've talked a little bit about this already, so I just want to remind you that energy, we can define energy as the capacity to do work. And that's nice, talking about having a specific definition for what is energy and what it means. But it leaves another question, and that's what? So if energy is the capacity to do work, then what question do we have? How about what is work, right? You're like, okay, well, energy is the capacity to do work, but how do we even measure work? What does that even mean? And so work is force executed across some distance. And so we can measure the amount of work done on an object by figuring out how much force it took to move that object, to overcome whatever was holding that object in place, and how far did that object actually move. So there are a lot of ways you can do work. You could talk about the work that a car's engine does as it moves the weight of the car over some distance. Or you can talk about the amount of work people do as they push a crate across the floor, or even combining those two, which I think I did with our example problem of a car moving a crate, where all of the car's kinetic energy is converted into work done on some object. And so now as we have an idea of, okay, well, what work is, we have this formula for work. Work is equal to force times distance. Force executed across some distance. So work is equal to force times distance. What is the unit for force that we often use? Yeah. What's that? Velocity. So force, it has, force, remember, is mass times acceleration, right? Force equals ma. Mass is measured in kilograms. Acceleration is meters per second squared. And so our units for force are kilograms meters per second squared. Also known as what? Newtons, right? Named after the person that gave us all of our laws about how force transfers. And so the units for force are newtons. What about the units for distance? Meter. And so force times distance is a newton times a meter. And what unit represents a newton times a meter? Joules. Remember? So joules are kilograms meters squared per second squared, or newtons times meter. Saw that a couple of weeks ago. And so then the units for work then are newtons times meters, which equals joules, which is the same as the units for energy. Which makes sense because energy is the capacity to do what? Work. So they should be measured in the same units, and they are. And where this connects to what we've been talking about over the last couple of weeks is that we can use kinetic energy to do work. If something is moving and has some velocity, we can take that object and the energy in that object moving and actually use it to do work. And I mentioned this already, but I don't know if all of you were here, but I don't have an expo marker. So I'm actually going to solve these problems on the slide, and it will project it up there. We'll solve them the same way. It'll just require me sitting down rather than standing up. And so if that bothers you, I'm sorry. But we'll still solve all these problems together. So are there any questions about this as we kind of reviewed the idea of energy and how it's connected to work, what work is, the units for work, units for energy, anything like that? It'll start to make a lot more sense once we start solving some problems. All right, so here's our first one. If all the kinetic energy in a 135.5 kilogram person running at 5.00 meters per second is put into moving a crate 10.0 meters, how much force was exerted on the crate? Okay. So we have a few measurements provided for us in this problem. So let's get our pen. All right. So what do we have? Let me see if it'll let me do this. Yes. Okay, so what do we have? Or what are we given? Mass. Yeah, we're given mass. Our 135.5 kilogram person again. Okay, what else are we given? And I know it's not pretty, but I'll get better as we move along. What else are we given in addition to mass? Velocity tells us this person is running at 5.00 meters per second. So that is the velocity. Anything else? Yeah, distance, right? It tells us that the kinetic energy in this person is put into moving a crate a particular distance. So distance is equal to 10.0 meters. All right, so tools. So we obviously have the tool that we just mentioned, which is work is equal to force times distance, right? We have that tool. But we have some additional information here, which clues us into that we may need some other tool. Right, we've got mass, which is good because mass is part of force. But we also have velocity, which I guess is indirectly part of force. Force is mass times acceleration. And we have distance, so we've got distance accounted for. But then we have to remember that this problem is telling us something about kinetic energy, right? And we have to remember that kinetic energy is the capacity to do work. So we also have our tool for kinetic energy. Kinetic energy is equal to 1/2 mv squared. And that's nice because now that tool uses our mass, it uses our velocity, and it gives us kinetic energy. And the problem told us that all of the kinetic energy is going into doing work on this crate. Do you see that? All of the kinetic energy says, if all of the kinetic energy of this person was put into moving this crate 10 meters, what was the force exerted on the crate? So basically told us all of the kinetic energy was put into work. Well, that's cool because energy is the capacity to do work. And that's exactly what this energy is doing. It's doing work as this person does work on this crate. So now let's figure out what this problem wants, okay, what we want. Hey, put the A back. The A does not want to stay. Why? It doesn't want to stay. Oh, okay. Well, we'll just leave it as W blank NT. So what do we want? The problem's asking us what? Force, right? So it wants us to rearrange this tool to solve for force. So we can do that by dividing both sides by the distance, right? And so we know that force is equal to work divided by distance, which is 10 meters. And we know what about our work from the way this problem is set up? What provided that work? What's doing the work on this crate? Yeah, the kinetic energy of this person. So which means that force is also equal to, if it's equal to work over 10 meters, it's equal to 1/2 mv squared, which is 135.5. Okay, I'm going to keep doing it this way. It doesn't like my finger. 135.5 kilograms times the 5.00 meters per second squared, because it told us all of the kinetic energy of this person is going into work, which means we need to figure out the kinetic energy of that person, which is 1/2 mv squared. You okay with this so far? It's a little weird because it wasn't just as straightforward as taking one tool and plugging in everything we knew. We actually had to use multiple tools. We had to pick up the clues that the problem was giving us, telling us that we're putting all of the kinetic energy into doing work. So we have 1/2 times 135.5 times 5 quantity squared divided by 10.0. And the fewest number of significant figures we have in any of our variables is 3, meaning we need to present our answer in 3 significant figures. And we are going to get 169. And now we need to figure out what our units are. So this squared is going to come down and make this meters squared per second squared, right, units-wise. The meters down here will cancel one of those, and so we should have 169 kilograms meters per second squared. And that's nice. Why? What's another way to write kilograms meters per second squared? Newtons. And what is Newton a measurement of? Force. And what was the problem asking us for? Force. So our units make sense, implying that we did it correct algebraically, right? So 169 kilograms meters per second squared, or newtons, or 169 newtons. So that's how much force was exerted on this crate that was pushed a distance of 10 meters if it took all of the kinetic energy of the person to accomplish that, moving the crate that distance. And so now we've given some idea to what we can accomplish with that kinetic energy. It's like, oh, wow, well, that's cool. You've got a 300-pound person running at about 10 miles per hour. But what does that actually mean? Well, it means you can take a crate that is basically, you know, has a weight of 169 newtons, and you can push it 10 meters, 30 feet. You might think, well, that's super. Then what does that mean until you actually have a giant crate that you need to move somewhere? And then it's like, well, what do? Get a really big guy and have him work really hard to move this crate, right? It's one of the reasons why you make friends with big people for when you need to get big jobs done, right? You don't make friends with big people to eat meals with them, right? Because that's always dangerous. Make friends with big people to get big jobs done. All right, any questions on this one? Do another problem where we'll work through energy, work, this whole dynamic, and then we'll move on to just kind of talking about, okay, well, what's actually doing work, and how do we put this into the context of thermodynamics? This is kind of weird for me, just sitting down and working through these problems, because my big fingers don't really want to write on this, but we'll make it work. All right, so if a 6.50 times 10 to the third, or sorry, not if 6.50 times 10 to the third joules of work is done while accomplishing a force of 5.00 newtons, how far did that force move the object? Well, how do we know an object had to move? Because that's what happens when work is done, right? Work is some force executed across a distance. Until we figure out another way of figuring out work, and that's what we'll do in January when we complete this idea of thermodynamics. All right, What do we have or what are we given by this problem? Come on, what's there? I'm lost. Explain it to me. Work. I love it. How much work is done? 6.50 times 10 to the third joules. And at this point, as always, you could leave it in scientific notation, or you could convert it if you are not comfortable with scientific notation. Since our exponent is positive, if you want to get it out of scientific notation, your number should get larger, right? And if your exponent were negative, your number would get smaller. So if you wanted to actually take this out of scientific notation, you would just move the decimal place over 3 times, right? And so we could also write, or 6,500 joules. Either way, whatever you want to do, whatever you feel more comfortable with. All right, anything else? I'm lost. Find me. Anything else? Yeah, gives us force. And what is force? 5.00 newtons. All right. Tools. Well, we just introduced a new tool that we've started using and we've had a lot of fun with so far. Well, writing letters is really challenging. So tools, we have work is equal to force times distance, right? This new tool that we just got introduced to, we've already used once. We're going to use it again. All right? Does the problem give us anything else? Not in the way of variables, right? And so now what do we want? Yeah, we want distance. So we're going to need to solve this tool for distance. We'll divide force away from both sides. And so we get distance is equal to work divided by force, which equals, our work is, I'm going to do it as 6,500 joules divided by our force, which is 5.00 newtons. And we get basically 130. Let's figure out how many significant figures we should have, though. So 6,500, it started as 3 significant figures, right? 6.50. So writing it as 6,500, we just want to make sure we still had 3 significant figures. 6,500 looks like 2, but we knew originally we had 3, and then 5.00 newtons is also 3, and so we should present our answer with 3 significant figures, which would be 130. Put the decimal place there. And then let's figure out what our units are. Joules divided by newtons. What is another way to write joule?
Kilogram meter squared per second squared.
Sure. Yep. What's another way to write joules? Newton times meter. Right? Newton times meter, we'll cancel the newtons out. And what are our units? Meters. Why is that nice? What did we want?
Distance.
And how do we measure distance?
Meters.
In meters, implying our algebra was correct. Okay? Which is always nice. So we were able to move whatever that object was, 130 meters, if we do 6,500 joules of work on it, accomplishing a force of 5 newtons. 130 meters, no big deal, it's about 400 feet. But it's probably not that big of an object if it only took 5 newtons of force to move it. All right? Any questions, thoughts, concerns?
Wouldn't it be 13
Yes. Yes, it would. Nicely done. I tried to do it in my head instead of doing it on the calculator. Yes, it would. So let's erase this. And we'll try it again, a second time. 1,300 meters. And this is where it's interesting, because how do we present three significant figures in this? You can't unless you write in scientific notation and you wrote 1.30 times 10 to the third meters. So we moved to 1,300 meters. Even less of a big deal, only about 4,000 feet. All right? Questions? Now. Thank you, Isaiah. Okay, I can stand up again because transition to our next framing question. So what is getting worked on, right? We're talking about, okay, well, there's some object moved, 1,300 meters, or there's a crate moved by 135.5 kilogram person, 10 meters. But what is it that actually gets worked on? How can we make this to where no matter what it is doing the work, that we always basically refer to this setup in the same way? First of all, just to put this in context of all what we're talking about, this week is called the First Law of Thermodynamics. And so it's helpful to know that thermodynamics is the study of energy transfer. How does energy transfer? Where does it go? And even also, how does it change from one form of energy to another? So this is what thermodynamics is all about, studying energy transfer. So in the two problems we've done so far, energy transferred from the person, right, with their kinetic energy into the crate to move it over a distance of 10 meters. In our second example, energy transferred from whatever was doing the work to this object that was moved 1,300 meters. So when discussing energy transfer, converting from kinetic energy of one object into kinetic energy of another, or using kinetic energy to do work, we must have some kind of a reference object, something that we're referring to, that we're wrapping our focus around. Which this is why it's always interesting, when somebody asks the question, oh, well, how fast was that object traveling? Any of you watch baseball? I know you watch baseball, Micah. Micah and I share a love for the Dodgers. Micah and I were both very sad when they lost Game 7. But I've recovered. I assume he has as well. Seems young and resilient. Okay, anybody else watch baseball? Okay, we got another baseball. Nice hat. Love it. Iffy. All right. So in baseball, you oftentimes see where they'll show you the speed of the pitch, right? Somebody will throw a fastball, and you're like, no big deal, 100 miles an hour, right? No big deal, Aroldis Chapman, 103 miles an hour, right? No big deal. It's always interesting because without referencing that movement against something else, that velocity is really meaningless, right? Because you're like, well, with regards to what? And basically in that it's implied and goes without saying that it's basically in reference to the batter, right? Who should not be moving at that point. And so in reference to the batter, the baseball is traveling 103 miles per hour. But if you were to refer the travel of that baseball to something else, things can be different. And this, you see it especially in vehicles and cars. So if you're in a car driving 75 miles per hour and you are passing a car that is going 70 miles per hour, compared to that car, you are only going 5 miles per hour, right? Because it's traveling at 70, you're traveling at 75, so compared to that car, if you're traveling in the same direction, you are moving 5 miles per hour. After an hour, you should be 5 miles further ahead than that car that's driving 70 miles per hour. Okay? And you're like, oh, well, obviously it goes without saying But in energy transfer, it doesn't go without saying. You need to reference what it is you're talking about. Otherwise, it gets very confusing. And you start having questions about what should the sign be. Should it be positive? Should it be negative? But if you keep everything sorted out, it helps out a lot. So our reference object, we call this the system. So we call whatever that reference object is, basically whatever brought energy to the problem, we call this the system. Everything else is called the surroundings. Okay, so you have the system, whatever that reference object is. Everything else is called the surroundings. And then the system and the surroundings together is called the universe. And you're like, well, I guess that makes sense because that's literally everything. Because you've got your system, whatever that reference object is, surroundings, everything else. And so everything together, system and surroundings, is the universe. And so in these thermodynamics problems, it helps out a lot if it's the system that's doing the work. Okay, if the system is doing work on the surroundings. So get into the habit of doing that. When we set up problems and we say, okay, well, this object does this amount of work, just whatever it is that's actually doing the work, set that as your system. And reference everything off of that. It makes all of our equations work a lot neater and tends to make it a little bit less complicated as far as what the sign should be on your calculations. And so we have this formula here, and it's a little disappointing that they use a U because in thermodynamics, the universe refers to everything, right? And you're like, oh, U is for universe, and it's not. U actually represents the total energy in the system, okay, and what is doing the work. Okay, so U is the total energy of the system, not the universe. Q is heat absorbed by the system during this process. And then W is the work done on the surroundings. W is work done on the surroundings. And again, this week we're just kind of laying a foundation of thermodynamics. And then it'll really start to, hopefully, everything will start to fall into place in January when we meet up to do lesson 10 together. Isn't it crazy that this is the last time we're meeting together to have a lecture? And then next week's the last time we're going to meet together at all this semester. And that may not seem crazy to you because you're like, well, it's already December. Well, I mean, what do you want from me? But it's crazy for me just how fast this semester has gone by. It happens. The older you get, the less 3 months, is relative to the amount of time you've lived. When you're a kid and you've only lived 4 or 5 years, 3 months is a long time. When you're an old man like me, 3 months isn't as long compared to the amount of time you've lived. All right? Any questions about this? And I know it's a little bit confusing to use U because we're just talking about universe, and U does not refer to the universe, instead refers to the total amount of energy. Now I'm going to set up problems to illustrate this concept that if you really want to pick it apart, does it make sense? Because we're actually going to have a car that during a collision absorbs heat, which it would, but not the amount of heat that we're making it absorb. But that's because I want to use real world objects that you can think of, like, yeah, I could picture a car colliding with something. Whereas in January, we'll start to talk about heat transfer and start to use fluids and fluid dynamics. And we'll talk about, okay, well, let's say you had this collection of water that absorbed this amount of heat. How much work could it do? And then that's a little bit different. All right? So I say that to, if we put into a context and a car in a collision absorbs an enormous amount of heat, I don't want you to be like, well, how does that make sense, Dr. Engel? How would it absorb that amount of heat? And I will answer that question as saying it wouldn't, but I wanted to use a kind of a real life scenario, even if what I'm setting up is not possible. You're like, what did this car have this collision on the sun to absorb that amount of heat? Just relax, okay? All right, so our first problem. This one just very non-focused, very generally. What is the total energy of a system that does 5.65 joules of work while absorbing 14.5 joules of heat? Okay. All right, what do we have? Or what are we given by this problem?
Work.
We're given work. All right. Work is equal to 5.65 joules. Yes? What else are we given? I'm lost. Help me to find my way. I've been doing that all day, and I don't know why, but I've been having a lot of fun just speaking in monotone. This morning I was like, I have forgotten. Would you please remind me? What do you got for me, Zion? Heat, which is Q, is equal to 14.5 joules. All right. That's it, right? Anybody see anything else? Any other variables that the problem gives us? I do not. So let's go to tools. We just got introduced to a new tool that says U, which is equal to the total energy of the system, is equal to Q, heat absorbed by the system, minus W, work done by the system, right? Just learn that tool. All right, what do we want? Yeah, this is awesome. We want U, which our tool is already set up to accomplish. We want U. Basically, what this problem is asking us for is how much energy did the system absorb in this process? So the system, whatever it is, our point of reference, absorbed a lot of heat, but actually did some work. So its energy increased by absorbing heat, but it lost some energy in doing work on something else, transferring its energy to some other object to do work, to move it over some distance. And so basically we're saying, okay, well, how much did its total energy change? So sometimes you'll see this referred to as delta U, which is the change in total energy. Okay? Not always. Sometimes you'll see it referred to as delta U. All right? So what is Q? 14.5 joules. And then we're going to subtract away our work, which is 5.65 joules. And when we are doing adding or subtracting, we don't worry about the number of significant figures. We worry about the number of decimal places. This has one place after the decimal. This has two places after the decimal. And so our answer should only have one place after the decimal. And so we get that U is equal to, what would this be, 8.9 joules. But I need to check that because I already did my math wrong once. 14.5 minus 5.65, we get 8.85, but we can only present our answer with one decimal place, so we need to round that up to 8.9. So 8.9 joules. And so again, what that means is that's how much the energy of our system changed. It absorbed energy. It absorbed a lot of heat, did some work, so lost some energy to do work, but overall its energy increased 8.9 joules. What's another way to write joules? Newton meters, right? Which means there's still a lot of capacity there to do more work, which is good because that's what energy is. Energy is the capacity to do work. All right? 8.9 joules is not all that much energy, but it is some. Any questions here? Is it hard to read? These letters that are all crooked and squiggly. Okay. All right. How much work can a system do on the surroundings if it has 0.65 kilojoules of total energy and absorbs 1.25 kilojoules of heat? And so basically what this question is asking is, after this, whatever this round of energy transfer is, that our system gained energy, right? You see it's got a positive total energy. So it gained energy, but it absorbed heat in that process. We want to know how much work it did, or how much work it could have done. You know, that's assuming, of course, everything was as efficient as it could possibly be. Which nothing is ever as efficient as it could possibly be. I forget efficiency ratings on modern internal combustion engines, but I think they're somewhere around 20%. For some reason, that number is what's coming up in my mind. Which means, if that's true, about 20% of the energy in the gasoline that you're burning actually goes into moving your vehicle. The other 80% is lost as heat, wasted. Unless, of course, you're standing next to said vehicle and it's cold outside, then that heat production is not wasted, right? It's appreciated. I feel like I'm rambling. Let's do this. What do we have? What are we given by this problem? Yeah, so we're given U, and again, sometimes you'll see that as delta U. U is equal to 0.65 kilojoules. Now we're talking about some energy, kilojoules. Each kilojoule is 1,000 joules. So we're talking about a decent amount of energy. What else do we have? Heat, right? Which is Q. Q is equal to 1.25 kilojoules. Okay. All right, tools. We just got introduced to a tool that seems like a good tool for our setup, because our tool includes both U and Q. U is equal to Q minus W. All right, what do we want? Yeah, how much work could have been done, right? Or how much work was done if this process was 100% efficient. So we want work. Well, all we need to do to manipulate this to solve for work, right now work is subtracted away, so let's go ahead and add it to both sides. Oh, I don't want to put it there. That would be confusing. Plus work over there. So then we'll have U plus W is equal to Q. That's not exactly what we want, because we want W by itself, right? So we can solve for it. So now we'll subtract U away from both sides. And we'll get that W is equal to Q minus U. Sound all right? Okay. So work is equal to Q, which is 1.25 kilojoules, minus U, which is 0.65 kilojoules. And again, we are subtracting again, so we are not concerned with the number of significant figures, although they both do have 3 significant figures. We are concerned with the number of decimal places. So we'll do 1.25 minus 0.65, and we will get 0.60 kilojoules. Make sense? Which means if this system absorbed 1.25 kilojoules of heat, or 1,250 joules of heat, it could have done as much as 0.60 kilojoules of work, or 600 joules of work, and still have that net energy increase. Now, it's still increased energy, meaning it could have done more work to still come back at the place where it started, but this is the amount of work that it could have done in this scenario. Okay, any questions? So in the homework, I'll have some problems where I will connect this to kinetic energy, like I did in the previous example problems where we had kinetic energy and all of the kinetic energy was converted into doing work. And then we'll kind of take this and say, okay, well, if it did this amount of work while absorbing this amount of heat, what was the net energy loss or gain on that car? And what you'll find is that car will have a net energy gain, which I guess makes sense in the event that this car was involved in a collision. It probably did have a net energy gain, and that energy went into crumbling the metal or plastic or fiberglass, whatever it was that was making up the car. All right. If there aren't any questions, I wanted to spend a little bit of time talking about exam 2 that I just handed back to you all today. So before that, I just want to make sure that there aren't any questions here. And if there aren't, I'll go ahead and stop the recording, get this all ready to send out to you. Okay. I will keep those. Thank you.